So data is given. I will be drawing from the single line diagram, I will be drawing the positive and negative sequences. We don't have any problems, but only the problem is with negative sequence. So you can take reference on top, reference on below. It doesn't matter at all. Okay. Now, let's talk about the positive sequence. So positive sequence, we have generator. Generator will be represented by sorry. You can take it up. You have to draw. Values, I'll put it okay. रेफरेंस आप कहीं भी रख सकते हैं, ठीक है। आज मैं रेफरेंस नीचे रखता हूँ, कोई ये कहेगा सर इसमें कोई फर्क नहीं है. This is for the generator number 1. Then we have a transformer. Positive will be represented by reactance only. Transmission line by reactance. Transformer by reactance. Then what we have? We have another motor. Motor we will be having. Sorry. We will be having the voltage source and then reactance. So neutral will not have any effect on this one. Okay. So now ground is below, so we can use this. Okay. And here also we will be having the voltage source. Okay. So values I will be writing. This will be plus minus a voltage source, generator 1, plus minus EM, whatever is the name, EM motor. So then we have for transformer 1 positive 0.1, and for that transmission line 105, this all are in per unit, and then for the transformer 2.1, you can have a look there also. Generator 1 point, what is the positive generator 1? Sorry, generator 1 is positive is 0.15. Why we are writing then? Yeah, it's 0.15. This is 0.15. Okay, fine. And what is the motor? Motor we are not written. Motor is 0.2. J.2. And then you can see transformer T1, T2 has same X 0.1, 0.1, transformer T1 and T2. Yeah, X1 is 0.12. Okay. But that is on the different base. We will calculate it. I'm just drawing the diagram. In zero sequence, I will clear what should be the values. Values, we will get it like this. Okay, file copy for the negative. These value we have to check because these are the different bases. So we have to check the base values. I'll be calculating that also. Okay, so we need to just a second. This we can copy and we can paste it here. Okay, so in case of negative sequence, we will not have this voltage source. Okay, so this is negative secants. Network, and this was the positive secants network. Okay, so let's move to the 0 seconds network. Now 0 seconds, we have to see the base values first. What are the base value he's trying to? Base value is 100 MVA, 13.8 kV. So let us first calculate those, then we'll see the base values. So on base value, what we have to use? Base MVA is 100 and base kV is 13.8. Okay, in the zone of generator, wherever it is in the zone of generator. So base kV for the transmission line, you can see it here. We can calculate it. Base kV for the transmission line. Sorry, it's here. Base kV for 13.8 is in generator. See, you can see generator has 13.8. So base kV for the transmission line T1 and T2 will have 13.8, 130 secondary by primary. So it will be 138 kV. Okay, I don't need to calculate. You can calculate it yourself. So, but I'm just showing you. We have done lots of numericals on this basis. 138 kV. So per unit reactance of generator. Reactances of generator. So X1 will be 0.15 per unit. X2 will be 0.17 per unit. And X0 will be 0.05 per unit. Since base is same, why? Here you can see 13 point is base kV. This so very same values we'll be using. So what are the values we have used? That are so positive we have used 0.1 for the generator, and that's all. Negative we have used 0.1 negative for the generator. For this we have used for the negative secants. So only negative secants what we have to take out the generator unit. So negative secants will be the same, but it is, I think, just a second, values correct or not. Yeah, it should be 0.17. We have to write here 0.17. Just okay, this is 0.17. Okay, I think motor is same. Just let me check. Yeah, motor all negative for the motor is 0.21. Yeah, 0.21. It's negative for the motor is 0.21. Let us check it. So these are the values given in the numerical itself. Okay, so we have to change the values, and then other values will be same for the negative secants. Let's add a page. Let's a page to this. Because this is the base kV for the transmission line. Per unit value for the generator will remain same. Why? Because the base kV both are same. Next we'll come to the per unit reactance of transformer T1 and T2. Of transformer T1 and T2. So let's see. So in this case, what's the values? Transformer T2 will have X1 is X2 is X0 is 0.12. So, but let's see they are in the same way, base or not. X1 is equivalent to X2 is equivalent to X0 is equivalent to 0.12 multiplied by, you can see here base MVA is here transformer 2-1. Base MVA is also different. We have a different base MVA. Also, base KV, transformer 2, sorry, transformer T1 or T2, both have same. So base KV on this side on the transmission line is different. On the generator side is different. So it's the same thing. We don't have to use them. We can. It's the same on both sides. So we will use just the MVA value. MVA is SB new is 100, SB old is 120. On that value will come out to be 1.1 per unit. Okay, that value is coming out to be 0.1. Now let's move for the motor now. Per unit reactance of motor M. Okay, per unit reactance of motor, we can see data is in front of me. X1 is per unit 0.2, X2 we have 0.21 per unit, and X0 we have 0.1 per unit. Okay, and also Xn we are having, that's the reactance. It's grounded through reactance. So here we can see the values. We can once again check motor X1, X2. X1 is 0.2, 0.21, 0.1, and Xn is 0.05. You can see these values. Now, okay. So what is the base values? We need to confirm what are the base values. Here base is 100 MVA or same MVA base. So on the 13.8 motor side, sorry, 13.8 motor side. So it is ratio is, yeah, it is 13.8. So it will be on the same. Only here it was, it has changed the base values. So here it will be same base values. So we don't need to both base values, that will MVA base value as well as the voltage base values are the same. So next is per unit reactance of transmission line. Of transmission line, that is, so X1 will be equal to X2, that will be equal to, so I'll be writing directly the formula V base line to neutral whole square divided by S base, that will be 20 into actual value by the base value. So everything I have written here, 138 square. You know these formulas, so I don't need to. So this will come to 0.0105 per unit, and X0 will be coming out to be 60 into 100 divided by 138. So that value is coming out to be 0.315 per unit. For those who don't remember, V base line to neutral whole square divided by S base. So actual value divided by this base value. V base line to neutral whole square divided by S base. S base will go up. Actual value is 60 and 20. So you have to multiply those values of just given here. You got to check it. I want to save some time. That's why I'm 66. I think this is 60. Yeah, this should be 60, I think. Okay. So that is the value we are getting. So now we'll be drawing the zero sequence network. Have a look at the zero sequence network. Let's say this is your reference value. Just zero sequence network. Okay. Somebody's 20 minutes are already gone. Okay. So now what we have. Yes, Moomin, tell me now how we'll draw the zero sequence. So generator is solidly grounded.
Yes, sir. उसको पहले हम reactance 1 से बनाएंगे.
So solidly grounded, there will be no reactance. There will be only what?
एक
There will
अपनी
be
generator
only
की reactance.
there will be no voltage source, there will be only generator reactance. So you can write it like this. So let us put it here like this. Sorry. Okay. So that reactance is solidly grounded. So solidly grounded means reactance is equal to 0. So we don't have to mention it. Okay. So we'll be considering only this reactance for the generator. And that reactance we have seen is in 0 sequence is 0.15. You can check it also. Just for your information, okay. This is 0.05 per unit reactance of the generator. We are writing just a second. Per unit reactance of generator is 0 sequence is 0.05. But how come? Just a second, let me check the data. 0.15, 0.17, 0.5. But why we are writing 0.5? Just a second, just a second. Generator 1, positive 0.15, negative, it should be 0. It's on the same base. See, we have seen here per unit reactance of generator, because they are on the same base, so value will be J.05. That's wrong. So value will be J.05. Whatever is given in the question that we have to write. Okay. Now moving ahead. After that, what we have? We have a transformer. Primary side of the transformer is delta. So we'll be moving like this. Just have a look how we can draw this. Okay. हेलो वालेकुम सलाम. हाँ, आप इस टाइम फोन क्यों कर? आपको 20 मिनट बाद आप क्लास ज्वाइन कर रहे हो तो कैसे अटेंड करने देंगे आप? चलो. ये कौन है? मोमिन 49, सबिया हुसैन.
सर सारे बच्चे क्लास के लिए.
Why they are coming late? Okay. So next is we are getting disturbed. इससे disturb हो जाता है. So primary, let me draw this winding here. Okay. For the transformer. Transformer की winding कैसे होती है? You can have a look. Sorry. So this is the way we have series switches, and then we have shunt switches. Okay. Now in this case, what is happening? Just a second. Yes. This is now, you can very clearly see series. What is this one? Series switches will be opened and shunt switch will be closed. So we will take a reactance here. We'll draw a reactance here. That's for the transformer. Series switch will be opened and this shunt switch will get closed. Obvious reasons, because winding on the primary side is delta connected. Series switch will be opened, that I have already told. So how much value will be there for the 0 sequence? The value for the 0 sequence will be, what's the value of the transformer T1? It's given here. Here we have to check it. Maybe it's, yeah, it is all the 0.1. So J.1 will be there. because they are on the new base. So that value will be J.1 per unit. Now move to the secondary side. Secondary side is what? Transformer T1. Transformer T1, it's star connected, neutral grounded. That means series switches will be closed and shunt switch will be opened. So we'll close the series switch here. So we'll be drawing this series switch. Series switches will be closed. And second is transmission line. Transmission line is represented by reactance only. So we can represent that by the reactance. So transmission line is here somewhere we have got J.13, J.315. Yes, this value we have got J.315 per unit. Okay, next is again the transformer. Have a look. So this is open here. Next is again a transformer. Again a transformer. So series switch will be closed and shunt switch will be opened because primary winding is star connected, neutral grounded. So let's have a look here. So I will be drawing the a bit series switches. Series switch I am going to close, and now I am drawing the T2. How much is T1? T2 is same. Yeah. Where is that one? This is for motor. Motor T1, T2. Yeah, it is same 0.1. So transformer is again 0.1 here. 0.1 in per unit. Now have a look on the secondary side of the transformer. Secondary side of the transformer is delta connected. That means again in secondary side series switches will be opened. So we have opened the series switch here. This series switch will be opened, but definitely the shunt switches will be closed. So shunt switches we can close here. This is a series switch which is opened here. And after that, what we are having? After that, we are having a generator that is reactance grounded. So in generator, we have the, okay, in generator, we will be having in generator, we will be having the reactance of generator and 3xn. Okay. So what is this? This is the reactance of generator and this is the 3xn value. So reactance of generator, zero sequence reactance, you can check it from here. Here, zero sequence is 0.05. Just a second. Oh, not for the generator, it's motor, sorry. Motor is 0.1. So this is 0.1. Motor is 0.1 per unit. And we have 3xn. 3xn value is given here. So xn is 0.05. So multiplied by 3. Motor you can see. Motor. Zero sequence 0.1 and xn is 0.05. 0.05 will be 0.15 multiplied by 3 we have to do. That we already know because of the zero sequence. It will have 3 into J.05. That will be J.15. So this is a complete network which is drawn for the zero sequence network. Okay. Now, if sometimes we can have a fault that can occur somewhere, we have to find the fault current in that case. So that will be another question. What's in the question, it is given or not? Calculate the per unit fault current for a three-phase to ground fault at bus D. So let's see what is the yeah, this is in the question. Bus D. So bus D is here. Okay, before the motor. So when the fault will occur there, So we will have to draw the, we have to find the fault current at the bus D. Is the voltage given or something given? Yeah, it is given. Pre-fault voltage is 1 point. See here. Draw the positive, negative, zero sequence networks with the reactor values in the per unit on 100 MV 13-1 base in terms of a zone of a generator. The pre-fault voltage is 1.05. So we will be using this network. Which network we can use? We can use positive sequence. That is J.15. Okay. And the fault can occur here, J.2. So you can copy this network. Just a second, it's hanging. We call this Thevenin's equivalent. So this we have to draw from the positive, because voltage source, only the positive sequence will be having the voltage source. No other will have a voltage source. So we have to draw from the positive sequence only. So let us copy it here. Okay. Then we'll take out this. What we are trying, when the fault will occur at, first let me write. When the fault will occur at D, then the positive sequence diagram during fault conditions is shown above. So, but what we have to do, we have to find as seen. This is a bus D is somewhere here. Can see. So we can see. Okay. So bus D is somewhere here as seen from this point. So pre-fault voltage is given as 1.05. So, but when we have to find this, again we'll read the question. Okay. The pre-fault voltage is calculate the per unit fault current for a three-phase to line ground at bus D. So bus D is here. This is the bus D. A, B, C, and D. We have to find at D. So let us find it at D. Okay, then what we have to do, we have to Thevenin's impedance when we have to find, so we have to short circuit the voltage source. So we will be short circuiting the voltage source in both the cases. So let us join them. Okay, so this way, let's add a page. And okay, you can have a look. So I will be writing here. So in this case, Z1 will be equal to J. These all are in series. These all up to here are in series. So that will be J.15 plus 0.1 plus 0.105 plus 0.1. So all are in series. I have added it because we have to see with reference to this. So it will be parallel with J point in parallel with J.2. Okay, so it is very, so that is called equivalent positive sequence. Z1 we called equivalent positive sequence impedance. That is your Z1. So therefore Z1, when we can calculate that, that will be J.455 multiplied by J.2 divided by J.455 plus J.2. That will come out to be J.193139 per unit. And therefore, this is the impedance. Fault current will be pre-fault voltage divided by the impedance at fault time. So that is 1 point that is given, J.193, and that should be J 7.558 per unit. So this is a very important question, and you can find anytime fault current, fault, the pre-fault voltages will be given to you. So this was another problem which was very important from the gate examination point of view. Then we have one more problem here. Not this. No. Okay. A three-phase generator rated. No, this is not. Yeah, a three-phase generator. Very important problem. This one also you have to find. A three-phase generator rated at 25 MVA, 13.2 kV has earth neutral. Positive, negative, and zero sequence impedance are given respectively. Resistance is neglected. Which value of the generator reactance must be placed in generator neutral so that the fault current for LG, fault of 0, fault impedance is not there, shall not be exceed the rated line current. So which value of generator neutral we have to find? Generator reactance must be placed in generator neutral. Along with the generator neutral, what are the reactance value we have to put? That we have to find. Then what is the value of the resistance in the network will serve the same purpose. So if reactance is not, then what is the resistance value which will serve the same purpose? Please have a look. This is also a very important numerical. One of the part can be asked in the gate type of examinations. So let's say we have a three-phase generator. So we have a star connected generator here. That earth has earth neutral. That means the reactance grounded is there. It is shown. So that's why we are telling the value of the reactance have to be obtained. So this is your okay. So this is your generator who has a reactance like this, and this we can have RY or AB, whatever you want to write, RYB, ABC, doesn't matter, but this is a neutral reactance Zn. Okay. What is telling us, three-phase rated at ITNA has earth neutral. We have seen that through reactance. Positive, negative impedances are given. So a rated current for the generator, first we'll find. Rated current of the generator is 25 into 10 to power of 6 divided by under root 3. And what is that? It's 13.2 or 13.2? Yeah, 13.2 into 10 to power of 3. So you can get this rated current as 1093.47 amps. Simply MVA divided by, because we are in line, so we have to get under root 3. This is a line value with whatever is the given value. Next is Z1 is given to us. Z1 is, I think, 30%. 40% and 50%. Yeah, it is 30%. So that means we can write Z1 0.3 per unit, Z2 is 0.4 per unit, and Z0 is J.05 per unit. Okay, and base impedance we can also find. Base impedance is V0 VL, sorry, V base line to neutral whole square divided by S base, and that value will be 13.2 square divided by S base is 25, that we already know. That value will be 66.97. Okay, so that's the base value in ohms. Z base will be, sorry, Z base is 6.97 ohms. Okay, now because we have which type of fault? We have line to ground fault. He has given which of the value of the generator must be neutral fault current occur. LG fault. LG fault, what we have? In case of LG fault, fault current is given as, fault current will be 3EA1 Z1 plus Z2, because it's what, it's reactance grounded, so 0 sequence will we have to add 3Zn, and ZF is given 0, no fault impedance, it's given in the question itself, it's given. Okay, so let us assume EA is 1 per unit. Normally pre-fault conditions are assuming that generator, assuming that we are always taking analysis like this. Analysis we are doing on no load. Generator is on no load. It's an unloaded alternator that we know. So IF fault current in per unit will be equal to 3 into 1 divided by Z1 is 30% plus 40% plus 50% plus this we do not know, 3Zn. This we do not know. That's what we have to find here. So the question is like this. Value of the generator reactance must be placed. So that we do not know, that we'll be getting. Okay, add a page here. So this is Zn. So here what we have, somebody can ask questions, sir, fault current is not given in this. Yeah, fault current is not given this. So please remember, if this type of question, that's why I have chosen this question. Which value of the generator reactance must be placed in generator neutral so that the fault current for the LG fault of zero fault impedance shall not exceed the rated line current. Rated line current is always 1 per unit. So fault current will be also 1 per unit. Rated current line is how much? 1 per unit. So that should not exceed that. So fault current will be, so we can here write, assuming, this point was very important point, assuming fault current IF equal to 1 per unit. So therefore 3 fault is 1, we can multiply this on this side. So we can write 3 is equal to J 0.3 plus 0.4 plus 0.5 plus J3Zn. Okay, so we can write this 3Zn will be equal to, because we are bothered about the magnitude, we need the magnitude, 3 minus, so that will be 0.3 minus 0.4 minus 0.5, and I think that is 0.5 or 0.05. That's 0.5, and which is equal to 2.25. So Zn will be equal to 2.25 divided by 3. That will be 0.75 per unit. Moment, is it clear or not?
यस सर, वहाँ पे 0.05 है, 0.5,
0.5 है 0.05.
0.05.
Okay, 0.05.
यस.
Okay, so we'll be getting this value, and that will be equal to 0.05. Actual value of Zn in ohms. Ohms base value we have already. Base value we have to multiply this. 5 into 6.97. We have got that previously. Ohms. So it will be 5.23. So second part of the question is over. Sorry, first part of the question is this is over. Now B part of this is what value of resistance. Now if the reactance is not, this should be very simple. Whichever the fault is there, get the base values, get the fault current. If fault current is not given, that has been given equal to rated voltage. Rated voltage is, sorry, rated current is always 1 per unit. B part of this is if the resistance is replaced by, sorry, not resistance, reactance. If the reactance is replaced by resistance, then what is going to happen? R for the same fault current. Okay, for the same fault current, the total impedance should be same in magnitude. Impedance should not change. Magnitude should not change. Total impedance will have same. So that means mod of Z1 plus Z2 plus Z0 should be equal to mod of J X1 plus X2 plus X0 and then 3Rn. Impedances will be same. So that Z0 here, instead of Z0, Xn will not be there, but 3Rn will be added. Okay. Again, assuming the fault current equal to the rated voltage, that means assuming the fault current IF equal to 1 per unit, then what will happen? Z1 plus Z2 plus Z0 should be equal to J 0.3, 30%, 40%, 50%, 0.5, okay, plus 3 Rn. This is in bracket. Why Rn? Rn is in real quantity only. Okay, so IF in this case will be, sorry, just a second, let me switch on the battery. Charge is not there. Okay, so fault current in per unit, we know in case of LG fault is same, EA1 divided by J 0.075, 0.75. Okay, it will be same. Plus will be 3Rn. Okay, 3 divided by 0.75 plus 3Rn, that should be equal to 1 now, because fault current is 1. Now here we can see, we can multiply this on the other side. So modulus, we can solve the modulus. Modulus can be solved like this: 3Rn whole square plus 0.75, because we are taking magnitude, 0.75 whole square will be equal to 3 square. Okay, so that value will come out to be 3Rn whole square will be equal to 9 minus 0.56. I think this will be square of this, and that will be 8.44. So therefore 3Rn will be equal to under root of 8.44. That will be equal to 2.91. So Rn value finally will come out to be 2.91 divided by 3, and that value will be 0.97 per unit. So therefore actual value of resistance should be 0.97 into 6.97. That's the base value. That will be 6.76 ohms. I think this was a very important problem. So you need to see the modulus values, how we have to take. This question can be done in this way only. It's a very important problem, sometimes asked in the examinations. Okay, so how much time we have left? Okay, then we had some gate problems also. I will ask the question. Okay, we have solved this. Okay. Just we had another problem also. We had a lot of problems to do, but time constraints are there. Okay, let's move to this problem. Now, in a power system, the three-phase fault MVA is always higher than single line to ground fault MVA at a bus. Is it true or false? Mansha, question is to you.
Yes, sir.
In a power system, three-phase fault MVA is always higher than single line to ground fault MVA at bus.
So this is false, I guess.
Why this
Because
is false? Yes, शाबाश, it is false. But why? Reason तो होना चाहिए ना, ऐसे तुक्का तो नहीं ना चलेगा.
sir, because in this case हमारा 3 times जो zero sequence current होती है in single line to ground fault.
No, this is about MVA. ये तो सीक्वेंस करंट के बारे में है नहीं. करंट के बारे में पूछ रहे हैं कुछ, हम कुछ नहीं पूछ रहे हैं. क्वेश्चन आपने पढ़ा नहीं शायद. थ्री फेज फॉल्ट एमवीए की बात कर रहे हैं. The reason for this is terminus of the generator LG fault is dangerous. Why? Number one, I will tell you why false. Why it is false? It is terminals of generator. When the fault occurs at the terminals of the generator, the LG fault is dangerous because the fault MVA will increase there. The fault MVA is going to increase. Now on the transmission line, triple line to fault is dangerous because all the three lines are down. Other three lines are touching each other or down. The fault MVA is more and current is also more. So it is the term always cannot be there. it is there. The three phase fault MVA is dangerous, but it's not always there. Why? Because if in the transmission line we can see a triple line fault occurs, it is more dangerous at that time. So sometimes it may not be there. So that's why it cannot be always true. That's the reason. Okay. So next is, okay, we'll be choosing a small numerical. आज time हो गया थोड़ा. So can you answer Rutba roll number? What is 27 is Rutba? She is there? No. Okay, Diba 48.
Yes, sir.
Can you tell me the phase sequence of a three-phase system is shown in figure? The phase sequence. What is the phase sequence of this one? What is the phase sequence of this one? हमेशा फेस सीक्वेंस क्लॉकवाइज होती है. अभी तक आप 6 सेमेस्टर में पहुंचे, इतना भी नहीं पता है. क्लॉकवाइज अगर आप चलेंगे, आर आएगा सबसे पहले, फिर बी आएगा, फिर वाई आएगा. आर बी वाई. फेस सीक्वेंसेस आर बी वाई. कैसे, ये आप देख लीजिए. जस्ट आई विल ड्रॉ इट समवेयर. Okay. So first cycle we will have R. Okay. Then second cycle we will have B. पहले एनकाउंटर कौन होगा? क्लॉकवाइज या फेज सीक्वेंस. आप R से चलेंगे B, फिर आप Y से. आप कहेंगे सर Y से, यहां से Y से नहीं जा सकते. यहाँ B फेज से जाएंगे, फिर होते हुए ऐसे चलेगा ये. क्योंकि यहाँ आपका फेज सीक्वेंस क्या बनेगा? B Y. अगर आप क्लॉकवाइज चलते हैं, यहाँ देखिए B Y R. मैं आपको ये बताता हूँ, एक मिनट, जस्ट सेकंड, इससे ड्रॉ करके आपको और क्लियर हो जाएगा. सो दिस इज गेट क्वेश्चन है ये. दिस इज वन ऑफ द गेट एग्जाम. बिल्कुल सिंपल क्वेश्चन गेट में पूछा गया है. ओके. ऑफ फेजेस में कह रहा हूं. देखिए आप कैसे, ये टाइम पीरियड है आपका. ठीक है, ये क्वांटिटी है आपकी, जो भी वोल्टेज या करंट जो भी क्वांटिटी दी होगी. सी नाउ व्हाट इज दिस आर. Okay, now second will be B, third will be Y, next will be R, next will be again Y, sorry, RB. Now this is matching always. See, RBY. If I will leave the first one, BYR, if I leave second one, YRB. Now here, if somebody can, sir, ये नहीं, पहले फेज B Y आ रहा है, RYB में लेता हूं, तो this will never match. क्यों? यहां से आप चलेंगे RYB से, फिर यहां से भी तो क्लॉकवाइज होना चाहिए ना, वही BY और R होना चाहिए, कहीं ना कहीं BY R होना चाहिए. देन अगर आपका फिर RYB आ रहा है तो वो तो गलत हो रहा है. See, now by RBY, how you can manage the actual R, then we have B, then we have Y. See, it will be always RBY, RBY, RBY. Now start from the phase B here. BYR, BY. Second से start करो, BYR. थर्ड से स्टार्ट करो. ठीक है, थर्ड क्या आपका? Y, YRB, YRB. This is the way exact. This is the way you have to write the phase sequences. अगर आप आर वाई बी रखते हैं तो यहां से जब आप जा रहे हैं आपको तो यहाँ बी वाई आर आ रहा है, तो वहां कहीं बी वाई आर नहीं आएगा. दिस इज द वे टू वेरीफाई इट. ओके, लेट्स से टाइम हो गया है. वी शुड हैव डन वन मोर न्यूमेरिकल. ये एक इंपॉर्टेंट न्यूमेरिकल है, आप घर में ट्राई कीजिए. ठीक है. 3 फेज आइडेंटिकल स्टार कनेक्टेड रेजिस्टर्स 1 पर यूनिट आर कनेक्टेड. ये भी गेट का क्वेश्चन है. ये आई थिंक IIT खड़गपुर से पूछा गया है. Connected unbalanced three-phase supply, the load neutral is isolated. The symmetrical components of line voltages are given like this. If all the calculations are with respect to base values, the phase to neutral sequence are. So you have to see this one. Okay. ठीक है. Okay, Moomin, you can send me the log now.
Yes, sir.
हो गया?
Yes, sir. भेजिए मैंने.
Okay, you can leave in a moment, no problem.